ba 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 director. Man, what am I doing?
Hello, and welcome back to another exciting episode of Mr. Bell Physics. Today, we are continuing our series on kinematics by talking about velocity and acceleration. Now, last episode, we talked about distance and displacement, and we had mentioned velocity briefly, but today we're going to go much more in depth with it. Now, kinematics, as I have stated before, is the study of motion. It's the science of motion. It's the ability to understand how things move in any given time. Velocity, though, is probably the biggest part of kinematics because it's actually the measurement of the rate at which things move. Now, to kind of put an example of this, as I mentioned before, position is ultimately something that all objects within the universe have. Right? I am at a fixed position right now. I have now changed my position, and I've changed my position again. Now, we talked about the change in position and how that can be either distance or displacement, depending on what you're measuring. Today we're talking about velocity, so we're only going to be using displacement moving forward. Now, velocity specifically is defined as the rate that position changes over time. So, to put that into perspective, okay, I can displace myself from my starting position by moving, like so, and like so. Right? But the rate at which I do that, how fast I do it, can change. So, for example, I could go like this pretty quickly, or I can really take my time with this, really kind of move slowly, right? I'm still moving the same displacement overall. But the amount of time that it takes me to do that is now much higher, which means that the rate at which I'm moving has gone down significantly. We can calculate exactly how fast I'm moving, a velocity, which is different than speed. Speed is distance divided by time. Velocity is displacement divided by time. By taking our change in position, x final minus x initial, so however our position has changed, whatever our displacement is, and divide it by our time. Let's do an example together. Okay. Now, the space that I just moved is about a meter, give or take. So, let's say I have a change in 1 meter. Let's say it takes me 1 second to do it, and then let's say it takes me 5 seconds to do it. Right? So, I'm going to do my work right here. Okay. As you can see, I've kind of prepped some stuff already on the board, trying something a little bit different with that. But we still have enough room to do our work. So, whenever we're doing a math problem in physics, we want to make a bit of a shopping list of our variables, okay? So to solve for v, we need 3 things. We need x final, x initial, and t. Now, I'm going to call x initial 0. And I can do that because I'm the one defining what 0 even is, right? There's nothing saying that it has to be at 0. Okay, this could be 1, this could be 10. It doesn't matter. But I'm going to call it 0 for simplicity's sake. And I'll prove why that doesn't necessarily matter later on. X final, we're saying I moved 1 meter, so therefore my final position has to be 1 meter. Notice I am keeping track of my units here, right? The standard unit for displacement, for distance, for position, for anything involving that is meters, okay? If you're given that value in any other unit, you must convert it, okay? And then finally, time. We're saying it takes me 1 second to do it for this first one. So time is going to be in 1 second, okay? Seconds is our standard unit for time, so that's all good. So now I can plug in. I'm going to use this kind of blank area in this graph here to do my math out, but I will erase it later. So V is going to equal x final, 1, minus 0, which is x initial, divided by time, 1. 1 minus 0 is just 1, divided by 1 is just 1. So therefore, V equals 1. However, there's an issue with this. See, the issue here is that 1 doesn't mean anything in this context, right? Unless I include something called a unit with this number, 1 is meaningless to me. It's just a number 1. 1 what? 1 year? 1 pound? 1 hour? Who knows, right? So I need a unit here. We can figure out the unit for velocity quite simply because we did a number in meters divided by a number in seconds. So our unit is going to be meters per second. Just like that. Now, that's not too bad. Let's do a bit of a weirder one, okay? Let's say I move that same amount of distance, but it takes me 5 times as long to do it. So instead of t equals 1 second, t now is going to become 5 seconds. And to prove that it doesn't matter if I use 0 or not, I'm actually going to change these to just have a difference of 1. So let's have this be 5 meters and this be 6 meters. This will change up our math a little bit, okay? So, you do it down here. Velocity equals x final, 6, minus x initial, 5, divided by t, 5. This one is not as easy to do in our heads as our 1 minus 0 is. So, let's show out the steps here. 6 minus 5 is 1. In the same way that 1 minus 0 was also 1. However, now, instead of being 1 divided by 1, it's going to be 1 divided by 5. Which, if we were to do it in a calculator, would come out to be v equals 0.2 meters per second. Don't forget that unit. So, that's how we can calculate velocity. But what does that number actually mean? What that number means is that for our top value here, that 1 meter per second, means that every single second that passes that I'm moving at this velocity, I am moving forward by 1 meter. Down here, it means that every single second that is passing, I am moving forward 0.2 meters. So, just by these alone, we can tell guy 2 down here is moving substantially slower than guy 1 is. But that also makes sense intuitively because covering the same amount of distance in more time, by definition, makes you slower. So, understanding the numbers is one thing, but actually understanding what do those numbers mean and how to plot those numbers is another thing. So here I'm going to turn to a graph. Okay, we're going to use this top graph specifically. This is a position versus time graph. So position versus time. Now, in the y-axis here, I have my position represented by the variable x. It's measured in meters. It goes from 0 to 20. Here in the x-axis, I have time measured in seconds. This is because with velocity, time is going to continue going on no matter what. But how far I've moved depends on what my velocity is. My independent variable will be time. My dependent variable will be position. Because time continues no matter what, whereas my change in position matters on what my velocity is. Right? Purely depends on that. Now, I'm going to get some new colors out. Let's get blue and red. And red should be over here. Yep, okay. And what I'm going to do is I'm actually going to draw some stuff out here, okay? So, let's say a dude was moving much, much faster than I was, right? Let's say he's covering 5 meters per second, right? So, over 1 second, he moves 5 meters. So, 1 second here, 5 meters here, make a dot, make a point, okay? 2 seconds, 10 meters. 3 seconds, 15 meters. Just adding 5 meters every single second. 4 meters, or 4 seconds, 20 meters. If I do my straight edge here, so I can actually have that graphed out properly. Should be something like this. I guess something that looks like that. Now, this is showing my position changing over time. The slope of that graph, right, how high it's pointed up, is my velocity. Okay? So in this case, over 1 second of time, actually let's do 2 seconds of time, change up the math a little bit. So over 2 seconds of time, so V equals divided by 2, because that's my time, I went from 0 to 10 meters. So 10 minus 0. 10 minus 0 is 10, divided by 2 equals 5. So my slope here is a slope of 5. Now that's cool and all. But let's see what a different slope would look like here on the same graph. Let's say I have a guy who's only moving half as fast. Okay, so it takes him 2 seconds to go 5 meters. So it would be here, and then 4 would be 10. Now yet again, I can take my straight edge, and I can line everything up like so. There we go. And as you can see, our slope looks substantially different. Our slope looks less, well, sloped, right? It's a smaller slope, right? It's more flat. What this implies is that our velocity should be less. So let's see if that's true. Again, we're going to do out the math, okay? We're going to do it the exact same way that we just did, okay? Velocity equals, we went from 0 to 5 meters, so 5 minus 0, in 2 seconds. So 5 minus 0 is, in fact, 5. Divided by 2 is 2.5. And you can double check that in a calculator if you really wanted to. So we covered half the distance, or half the displacement rather, in the same amount of time, which means that our velocity is exactly half of our original velocity. In other words, we're moving slower. Now, this all assumes that we are moving at a constant velocity. What if our velocity is changing? That's where acceleration comes in. And acceleration is a very, very important term in physics. It doesn't just stop here at kinematics, it shows up all over the place in physics. So the definition of acceleration, we'll get rid of that. Definition of acceleration is the rate that velocity changes over time. And our formula is pretty much the exact same one that we used for velocity. The only difference being that instead of displacement, we are now using velocity. So, let's take a look at a problem for this, okay? Let's say I'm running a race, and I start at that 5 meters per second from before, right? So let's say VI is equal to 5. But then I get tired, I slow down, right? I run out of breath. So my velocity goes down over time. V final, let's say, is our 2.5. And mind you, these are both in meters per second. Let's say I did that over a time of, let's say, 5 seconds. So if we do this math out, our acceleration is going to be equal to our final velocity, 2.5, minus our initial velocity, 5, divided by 5. Now, you may be wondering to yourself, Mr. Bell, Mr. Bell, Mr. Bell, this is going to give us a negative number. And you're absolutely right, it is. We did not make a mistake here, okay? See, a rate can be both positive or negative, okay? We haven't really talked about a negative velocity yet. See, in physics, these values are what we call a vector. A vector is just a number that has a magnitude, how big that number is, but it also has a direction, right? Positive or negative. So for these velocities, these are both positive, meaning that if we're calling, say, forward positive, I'm moving in this direction, right? And I'm moving and I'm moving and I'm grooving, right? But let's say we had a negative velocity. Instead of moving forward, I would move backwards, baby. Oh yeah. Okay. So all that negative sign is going to mean is which direction we're moving in for velocity. For acceleration, we're going one step even further, right? It's not necessarily if we're moving forward or backwards. It's are we speeding up or are we slowing down? So in this case, we're going to get a negative acceleration, which means that our rate of change of velocity is going to be negative. That means that over time we are losing velocity, which means we're slowing down. If we have a positive acceleration, that means we're gaining velocity over time, which means we must be speeding up. So let's do out this calculation and see what we actually end up getting here. So 2.5 minus 5 is going to equal negative 2.5, and that's going to be divided by 5. Doing that in our calculator, negative 2.5 divided by 5, I end up getting A equals negative 0.5 as my acceleration. Now, you may be wondering, what's the unit for acceleration? Okay, I made such a big deal about needing a unit for velocity. Surely we must also need a unit for acceleration, and you're absolutely right. The difference here is that we're dividing meters per second by seconds. So technically speaking, the unit should be meters per second per second. However, that doesn't really roll off the tongue very well. It doesn't really look very good on paper either. Mathematically, when you simplify that, what it becomes is meters per second squared. So our acceleration comes out to be negative 0.5 meters per second squared. Final answer. Now, again, all that means is that we're slowing down. This entire time, we're still moving forward because our acceleration is still positive. Or not our acceleration, our velocity is still positive. We are not reaching a point in which our velocity has become negative. As soon as that happens, we have turned around and started moving in the opposite direction. So, let's take a look at what this graph is going to look like. So, erasing the calculations here. What I have here is a velocity versus time graph. So instead of position versus time, this is velocity versus time. Velocity over here, represented by v, is measured in meters per second. Time down here, measured in seconds still. Okay, no real change there. Let's say, hypothetically, I was speeding up quite a bit, right? Let's say I'm really running hard. I'm really digging deep. I'm really sprinting here. Let's say, like my velocity graph earlier, my acceleration is changing by 5 every single second. So, taking my straight edge, I don't think I actually had this perfectly lined up, but that's fine. I can modify it. Maybe I had to tweak this a little bit, but that's fine. So this point should actually be on the line. This is why you should use graph paper for this kind of stuff. Makes your life way easier. So here, like before, the slope has a meaning, okay? All that I'm actually looking at right now is my velocity changing over time. The slope at which it changes time, or at which it changes over time, is my acceleration. So let's calculate what our acceleration for this example would be. So acceleration in this specific example would be A equals V final. So let's say we use it at 2 seconds. 10 minus V initial, 0, divided by 2. 10 minus 0 is 10, divided by 2 is 5. Therefore, this is moving at 5 meters per second squared. What does that number mean? It means that every single second, our velocity is increasing by 5 meters per second. Now remember, 1 meter is roughly 3 feet. So we're moving about 15 feet per second faster with every single second, meaning that we're actually moving pretty quickly here. Right? On average, people don't get too much faster than 5 meters per second squared. Okay? It takes a lot to accelerate faster than this. Now, again, let's do another example where we have a bit of a slower acceleration. Okay? And the reason why I'm showing you this is because the math here really is kind of the exact same thing. It just means different things. So let's say after 2 seconds, we've only gone to a velocity of 5. After 4 seconds, we move it up to 10. Okay, very similar to our last example with velocity. Bring that down slightly. There we go. So, again, our slope is lower, which means that our acceleration is less. Okay? Let's do the calculation again. Okay? Let's do it right at 2 seconds yet again. Okay? Acceleration equals, we went from 0 to 5 in that time, so 5 minus 0 divided by 2. I get 2.5 meters per second squared. Now, I know it looks like I just did some very repetitive math, okay? That basically all means the exact same thing. But the thing is, it doesn't mean the exact same thing. Physics oftentimes is oversimplified to be just a math class, and that's not the case at all. See, physics is a problem-solving class, where we use math as a tool to be able to solve a problem. So here, we can visualize what our acceleration and velocities actually mean by doing this. Now, I have one more thing I would like to show you before we're done. And that's what happens if we have multiple accelerations that we're dealing with. See, oh, we got announcements. Hold up. Or maybe we don't. Now we do. I guess they're looking for a custodian. Now, for this example, we've been looking at problems assuming we have a constant acceleration, assuming that acceleration does not change over time. I'd like to look at an example where acceleration does change over time. So let's erase all of this. Bear with me for a second while I do that. While I'm doing this, why don't you tell me how your day's been going in the comments down below? I hope that you've been having a lovely day. I'm recording this on a Friday. It's just after school now, so I'm looking forward to going home pretty soon. But, of course, we're getting these videos done first because that's what's important here. All right, so brand new whiteboard. Let's get our velocity versus time graph up again. But instead, let's make it a little bit bigger this time. Make it a little easier for us to see. So making sure that I'm in line here. Yep. Now, this may look slightly crooked to you guys, but I promise you it actually is not. Okay, this is 100% level from my perspective. Okay. And yep. So what I'm actually going to do is I'm going to create two graphs. Okay, one of them, again, is going to be position versus time. One of them is going to be velocity versus time. And we're going to see what happens when we have a non-constant acceleration. Now, you may be wondering, why am I bothering doing this? Right? What difference does it make if we have an acceleration that's constant or not constant? See, in physics, it actually does make a pretty big difference. Kinematics and all the equations that we use for kinematics only works if we have a constant acceleration. So, this is going to be position versus time. If I can actually spell. And then over here will be velocity versus time. So, let's go a bit longer this time. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say 9 seconds here. Yeah, sure, why not? Four, 5, 6, 7, 8, and 9. I know they're probably not spaced out perfectly, but sue me. Okay, I'm doing this after school for your own benefit, so stop complaining. For position, let's go in increments of 10 meters here. So 10, 20, 30, 40, 50, let's say we go up to. And then velocity, let's also go in units of 10 here. Why not? 10, 20, 30, 40, 50. All right. So again, down here I have time. Over here I have position. Over here I have velocity. Now, let's say we have a non-constant acceleration. What does that mean? Okay? That means that over the period of time, we would not be moving at a uniform position. That means our velocity slope would change over time. Now, let's start off with velocity versus time, actually. That would be the easiest to start us off with, because that would tell us a story for this graph over here. So let's say for our velocity, we go from 0 to 10 meters per second in the span of 2 seconds. So 10 or 2 comma 10 will be our first point there. Then let's say we crank that all the way up to 50 meters per second. Actually, no, 40 meters per second at 5 seconds. Then we hold steady at that until 7 seconds before going all the way back down to 0 at 9 seconds. Now, what you may notice here is that we're not going to have a straight line. In fact, we're going to have multiple lines. So we go from here to here. Then you go from here to here. Then this is supposed to be held level. There we go. And then all the way back down to here. So this is what our velocity versus time graph looks like now. Now, as you can see, it looks kind of funky, right? And that's to be expected here. Okay, our acceleration is changing. What the slope changing means is that we are actually changing our acceleration over time. Now, we can tell if we're speeding up or slowing down based off of the direction of the slope. So long as our slope is positive, we are speeding up. So here, we're speeding up. Here, we're definitely speeding up. Up here, our slope is 0. We are not rising at all, which means that our velocity is constant. So no acceleration there. And then down here we have a rather strong downslope. This means that our acceleration is very rapidly going straight to the ground. Oh, surprise cut. Now, Mr. Bell made a mistake, so he had to start recording again. So here we have our velocity versus time graph. And what I've done here is I've actually shown where our accelerations are increasing and where our accelerations are decreasing or holding constant. So what we can actually do with this information is calculate what that acceleration is per each section. So let's go ahead and do that. So for section 1, okay, I'm going to call it section 1, section 2, section 3, section 4. For section 1, our acceleration formula is going to be our change in velocity. So that's going to go from 0 to 10. So 10 minus 0 divided by time, which is 2 seconds. So 10 minus 0 is 10, divided by 2 is 5, therefore acceleration 5 meters per second squared. Because that's A1. A2. We are now going from 10 meters per second to 40 meters per second. So 40 minus 10 divided by our time, in this case, 3. 40 minus 10 is 30. 30 divided by 3 is 10 meters per second squared. A3 is going to be 40 minus 40 divided by our change of time. We go from 5 seconds to 7 seconds. So 7 minus 5. And this really shouldn't be 3. This should actually really be 5 minus 2. My bad. There we go. Fixed. 40 minus 40 is 0. Divided by 2 is still going to be 0. So 0 meters per second squared here. And then finally, A4. This one should be negative because we are going from 40 meters per second to 0 meters per second. So final minus initial is our formula. 0 minus 40. And we're doing that from 9 seconds to 7 seconds. So this is going to give us negative 40 divided by 2, which is negative 20 meters per second squared. Now, we could also calculate how position would change over time with each of these. However, I'm going to save that for next time when we talk about calculating position with a constant acceleration. See, the math gets a little bit more tricky. And because of that, I think it's best saved for a separate video. Okay? That's the mistake that I made. I tried to do it all in one video. My bad. So, in the next video, expect to be exposed to our actual kinematic equations. Okay? The thing that makes kinematics one of the most difficult units in physics, or at least one of the most intimidating, we're going to unpack and solve together. So, until then, make sure you absolutely smash that like button, hit that subscribe button, ring that bell, okay, bell, get it? Funny. And as always, I will see you in the next video.